Okay, we're looking at section 3.3 again. This is using critical numbers in the first derivative test to find relative extrema. We're also going to relate that to graphing. Remember that critical numbers are the x-coordinates of possible relative maximums and minimums of a function. If we want to find critical numbers, the first thing we have to do is find vertical asymptotes. These are the values of x that make the original function undefined. These cannot be critical numbers. They can't be high points or low points if they're not even on our graph, if it's undefined. To find the critical numbers, we set the first derivative equal to 0 and solve. These are going to be critical numbers. We also want to find out where that first derivative is undefined. These are critical numbers unless they are vertical asymptotes. Vertical asymptotes win out over critical numbers. So we're going to make our charts. We've already done this once before. And so we're just kind of reviewing how to graph and do everything with this. So looking at this first function, I'm going to take that derivative, 2x minus 6, set it equal to 0, 2x equals 6, x is 3. So that's my critical number. So I'm going to go from negative infinity to 3 and 3 to infinity. I want to test any number in this interval. I could test negative 1,000,000 if I wanted, but it's a lot easier just to check 2. I need to check anything from 3 to infinity. I could check 1,000, but it's easier to check 4. I'm now going to plug these test values back into that first derivative. So when I plug in 2 times 2 is 4, minus 6 is negative. All I care about is negative or positive. Plug 4 in here. 2 times 4 is 8, minus 6. That's 2, that's positive. So this function goes from decreasing to increasing. If I have a function that goes from decreasing to increasing, I have to have a point right there where that slope is 0. So therefore, I'm going to have a relative min at 3, comma, back into the original. 3 squared is 9. 9 minus 6 times 3 is 18, and that gives me negative 9. If we weren't sure about that, we could always check it on the calculator. Probably not necessary, but if you wanted to. X squared minus 6x, we do our zoom 6. I can see that, and I already know that this is a parabola that opens up, and I can see that that minimum's way down there. I could just look at my table and look at 3, negative 9, and I can see that's the lowest value. Negative 9 is the lowest one I've got, so that's my relative min. Okay, on example 2, I'm going to take my first derivative, and we'll just graph that real quick. We'll just make this by 2s. 2, 4, 6, 8, 10. So 2, 9, negative 9 is about there. My y-intercept would be 0, 0. However far that is, this is going to be the same amount over. This should be a 3. So go over 3 this way. It's got to be symmetric. And so there's my picture of my graph. Okay, taking my first derivative here, I'm going to have 6x squared plus 6x minus 12. Setting that equal to 0, I can divide the whole thing by 6. Set up my double parentheses. So here's what I get, negative 2 and 1. So now I have 2 critical numbers. So I'm going to have to add on another column to my chart, because I'm going to have to go from negative infinity to negative 2, from negative 2 to 1, and from 1 to infinity. I can test any number in this interval. I'll choose negative 3. I'm plugging that back into my derivative. It's harder to plug it in here than here. I'm going to plug it in here. Negative 3 plus 2 is negative 1. Negative 3 minus 1 is negative 4. So I have a negative times a negative, that's a positive. So therefore it's increasing. I can plug in 0. That would be 2 times negative 1, that's negative, that's decreasing. I can plug in 2, that's positive, so that's going to be positive, so it's increasing. All right, so now just kind of looking at this function, it's going to go from increase to decrease to increase. So if it's going to go from increase to decrease, I have to have a relative max at negative 2, back into the original. Negative 2 cubed is 8. Negative 8 times 2 is negative 16. Negative 2 squared is 4 times 3 is 12. Negative 2 times negative 12 is 24. So I'm going to have 36 minus 16, and that's going to give me 20. So I'm going to have a relative max at negative 2. Make this go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And negative 2, 20. And then if I go from decrease to increase, I have to have a relative min at 1 comma, back into the original. 2 plus 3 is 5, minus 12 is negative 7. 2, 4, 6, 7. And my function has to go increase, reach that high point. My y-intercept is 0, 0. To decrease, and then back up to increasing. And so that's the way it's going to look. All right, on this last one, same kind of thing. This one's a little different, though. I'm going to look at my original function. Whatever makes that denominator 0 is going to be a vertical asymptote. So I have a vertical asymptote at x equals 0. So before I do anything else, I want to go ahead and graph that vertical asymptote. Okay, so now I'm going to find my first derivative. I have to use my quotient rule. Derivative of the top times the bottom minus the top, derivative of the bottom, all over the denominator squared. That gives me 2x squared minus x squared minus 1. So that's going to give me x squared minus 1 over x squared. So there's our first derivative. And so what I'm going to look at now is the fact that whatever makes this undefined could be a critical number, but it's already a vertical asymptote, so it's not a critical number. So I'm just going to set that numerator equal to 0. Bring over the 1, take the square root, plus or minus 1 would work there. So those are my critical numbers. So for my chart, I have two critical numbers. So I'm going to have to go from negative infinity to negative 1. Now, in my chart, I also want to put in my vertical asymptote. So I'm going to go from negative 1 to 0. And I want to go from 0 to 1. And I want to go from 1 to infinity. We already know 0 is not going to be a max or min, but it is a breaking point, so it's good to put it in there. I test some number in this interval, negative 2, plugging that into my derivative. Negative 2 squared is 4, minus 1 is 3. So that's going to be a positive over a positive. That's a positive. I'm going to plug in negative 1/2. Negative 1/2 squared is 1/4. Minus 1 is negative. The bottom's always going to be positive because it's squared. So I'm going to have a negative over a positive. That's a negative. From 0 to 1, I plug in positive 1/2. 1/2 squared is 1/4. Minus 1 is negative. Plug in 2. 2 squared is 4 minus 1. That's positive. So this is going to go increase to decrease. So at negative 1 then, I'm going to have a relative max. Anytime I go from increase to decrease, we have to have a max. So we have a relative max at negative 1. Plug it back into the original. That's going to be 2 over negative 1 is negative 2. Plugging in my 1, because I'm going from decrease to increase, so I have to have a relative min at 1 back into my original. 1 squared is 1, plus 1 is 2 over 1 is 2. Now look at this. So we have a relative max at negative 1, negative 2. And we have a relative min at 1, 2. It's kind of weird, isn't it? But here's what's happening with this function. It's increasing from negative infinity to negative 1. Then it's decreasing. So it has to be going up and then down. And for this part of the function, from 0 to 1, my function had to be decreasing. So it has to be going down. That's got to be the lowest point. And then from 1 to infinity, it's got to be increasing. So this is about what our graph's going to look like. It's not going to be perfect, but at least we have some idea. If I come back to the graphing calculator, I want to put in parentheses x squared plus 1, all of that divided by x, zoom 6, And you can see that that is what the function looks like. So one more time, what I did on this one is I had found those critical numbers. I used those in my intervals, but I also wanted to put that vertical asymptote in there because it's a divider of the function. So I can see my function went increase, decrease, then we had the vertical asymptote, the break in the graph, then we go decrease, increase. And so we can see that this point, this -1, -2, it's a relative max. For those points right in there, it's the highest. And this point right here is a relative min because for these points right here, it's a low point.